Welcome back, and let us resume our discussion on the sampling unit. So, the simplest sample and hold unit can be seen as a switch in series with a capacitance. We can call it the sampling capacitance Cs, and we have the switch signal which is turning on periodically at the rate determined by the Nyquist rate. And if I assume that this on duration is sufficiently small as compared to the overall sampling period, we can assume that this switch is getting on only for a very small duration, and in that case whenever for this small delta t the switch gets on, the Cs will be sampling the input signal, and when the switch gets off immediately after this t on, the capacitor should ideally keep that voltage stored, because there is no other path for the charge to get dissipated. So, that should be the ideal behavior of such a system when this delta t or the t on approaches 0. So, if this is my analog data coming in at different instances, if I am looking at the Cs, if I assume that these are the locations where this t on is coming, which are very narrow pulses, my output will be constant after each t on, and it will be changing only when the t on goes high, and corresponding to that the switch gets on. So, this will be something like close to true sample and hold. And so on. So, this is the output waveform, the staircase waveform that we are going to get at the Cs. Of course, in real time you will have an overall non-zero pulse width, and hence you may obtain a track and hold waveform whenever the switch is on. So, if I zoom out the waveform in the real scenario, if I look at the sampling pulses, they are going to be on for a finite duration. I am just zooming out the sampling pulses. So, I am not maintaining the scale between these two, assume that this is a different scale. I am zooming out the sampling pulses. So, the sampling pulse is on during this duration, and therefore, when the switch is on during that duration, the voltage at Cs will be a faithful replica of the V in ideally, and when the switch gets off, it will stay constant. Again, when the switch gets on, it will again try to track the input signal, and once the switch gets off, again it will stay constant. So, this is the waveform we can expect if we are looking at the track and hold scheme with a non-ideal switch. So, I have just assumed that I have just zoomed it out, and the sampling frequency is still very large. So, this is the duration in which the switch is on. Of course, if we want this entire sampling duration to be allocated to the digitization process, we would like to reduce this as much as possible. We would like to reduce the T on as much as possible, so that the A to D converter can utilize the maximum of this sampling duration in conversion of the analog signal into the digital value. So, it will be favorable to minimize it as much as possible, and also that minimization would require certain design consideration with this switch, what kind of sizing, what kind of transistor configuration we are choosing for this switch. So, let us look at the implementation of the switch using transistors, and the simplest configuration can be just employ a simple NMOS switch, and you have the Cs over here, and you are driving this NMOS with a pulse, and you have the V in over here. We know that for the NMOS, however, the maximum input voltage that you can sample is going to be equal to VDD minus Vt if the gate voltage, the clock voltage is having amplitude of Vdd, because the moment input signal reaches Vdd minus Vt, the Vgs drops to below Vt, and as a result the current in this switch will drastically reduce, and hence it will not able to follow the input signal fast enough. Because of leakage current, if you leak it for a long time, it may still be able to follow, but for a sufficiently fast sampling, it will not be able to carry the input signal over here. It will stop at Vdd minus Vt. And likewise, if we have a PMOS input or a PMOS transistor, there also we know the overall behavior. If you are having the input signal over here, as the input signal goes lower, the PMOS will try to discharge this capacitor towards Vin if the Vin is going lower, and the clock signal, of course, that you need to keep the PMOS on is 0. When the driving signal is 0 or the pulse is 0, then it will be turning on, and we know that in order to have sufficient current through the PMOS so that it can discharge this capacitor, this voltage should be at least mod Vt or mod Vtp. Therefore, PMOS can conduct at the max till mod Vtp, Vin equal to mod Vtp. Likewise, NMOS would fail if the input signal is going beyond Vdd minus Vt, or you should call it Vtn. So, if I plot the resistances of this NMOS and the PMOS switch, we have the curves. If I mark this point as say Vdd minus Vtn and this one as mod Vtp. So, how does the resistance of the NMOS switch look like? So, input, as we have seen in our case, can go all the way from 0 to Vdd. So, the input can range from 0 all the way close to Vdd. So, this is the point Vdd. And if I talk about the NMOS resistance, as the input voltage approaches Vdd minus Vtn, the Vgs reduces to 0. As a result, the resistance of the NMOS will be increasing very steeply. It will be entering into subthreshold regime. As a result, close to this point, you have the NMOS resistance peaking. Likewise, the same thing happens for the PMOS. This is your R of N. Likewise, if I talk about the PMOS, we know that if the input signal is lower than mod Vt, this is 0 for keeping the PMOS on. If this is 0 and input signal is lower than mod Vt, then once again the Vsg becomes too small and the transistor enters into subthreshold, and the current will be drastically reduced, and hence the resistance of the PMOS switch will be drastically reduced, and hence resistance of the PMOS will be peaking when the input signal is approaching mod Vtp. On the other hand, if the signal is large, then there is no problem with the PMOS. It can easily charge the capacitor from high towards for a higher signal. Likewise, for the NMOS, if the signal over here is low, that is also not a problem. It can easily discharge, because this is Vdd, and even the signal is low, you have sufficient Vgs. Remember, if the signal is going low, this becomes the source terminal for NMOS, and it will be sinking the current. It will be trying to discharge the Cs, and in that case, the terminal over here becomes the source, and in that case, you have sufficiently large Vgs for smaller Vin. Therefore, the resistance of the NMOS, if I say, keeps dropping for a smaller Vin. Now, if I for a good switch, I would like to have a overall resistance which is constant, and it makes sense therefore to combine these two. If I combine both NMOS and PMOS, then the overall resistance will be a parallel combination of these two given by the lower of the two, and therefore, if I combine these two, I have an overall resistance of the resulting switch given by the superposition of these two resistances. So, So, you have the overall resistance being the superposition of these two switches, and the value will be lower than the lowest, and as a result you are going to get a curve something like this, which is relatively constant over a wide range from 0 to Vdd, and therefore, we have a combined switch which can be termed as a transmission gate, a combination of NMOS and PMOS, where you can have a clock signal going to the gate of NMOS, which will turn it on, and at the same time you have the clock bar going to the gate of PMOS, because when the NMOS is turning on, you also need to turn on the PMOS simultaneously, and therefore, you need the inversion of the clock signal as a clock bar demarcated over here. So, in this case you can have an overall resistance across the switch which is remaining relatively flat across the entire input range, and it can follow or it can sample an input signal starting from all the way from 0 or going all the way to VDD. So, this can be termed as a transmission gate, which is very effective in sampling operations or analog circuits where we have constant sampling of analog data. So, now we need to look into the design consideration that we just discussed. We saw that in order to maximize the digitization duration, so that the ADC can exploit maximum of the sampling time, I would like to make this duration narrow, and that would imply certain constraint on the choice of the CS, the sampling capacitor, and also the switch. So, let us look at that. So, if I talk about the sampling circuitry consisting of the transmission gate, which is sampling the input signal V in onto the CS, we know that the overall on duration must be smaller than the RC time constant provided by the switch. Ultimately, as we have seen, the switch is going to have some finite on resistance given by the parallel combination of the R on N and R on P, and as a result, under on condition, this can be represented as R on of the switch, and you have the CS. And therefore, the time constant provided by this 1 upon R on times CS, the corresponding time constant RC should be significantly smaller than the on duration. Therefore, when we are trying to reduce the on duration by making the drive pulse narrower, we would like to make sure that the on resistance times the CS is giving us the time duration which is sufficiently smaller than the clock pulse, so that the signal over here is faithfully able to charge. Otherwise, you know that if you are having an RC time constant which is much larger than the input clock, what can be the result? So, you will be having a very narrow pulse with which you are trying to sample the input signal, and suppose the input signal is going high, the output signal will not be able to follow the step. So, it may stop at an intermediate point. The expected value ideally would have been a much larger value depending upon the jump between the V in, the previous and the current samples of V in, but the switch being large resistance, it will not be able to follow. It will have a large RC time constant. As a result, the final value that you are sampling will end up being smaller than the actual value. So, we do not want that. We would like to have the RC time constant of the switch smaller than the on duration. So, now what are the pros and cons of doing that? We can look at the overall CS as well. One option is that we can go for a smaller CS that may also allow us to reduce the dimension of these two switches, and therefore, both we have the independence to choose both the CS as well as the W of the switches. But now, we have to look at the overall operation in the off duration also. What happens in the off duration when the switch is off, and under that duration what is the role played by CS and the transistors. So, the ideal functionality is that during the on duration the input signal should be faithfully replicated on the CS as fast as possible within that on duration, and when the switch is getting off, the signal stored over here should be remaining stable, it should not change significantly, and we need to see what is the effect of the nonlinearities of the switch on this expected behavior. To do that, we can first of all look at the off duration. For example, what is going to happen if the switch is getting off, and what is the behavior expected for the signal stored on this CS. So, when the switch is off, we have the NMOS gate voltage 0 and PMOS gate voltage VDD. Remember that source and drain definition of NMOS and PMOS of course are interchangeable depending upon the polarity or the sign of V1 minus V2. So, I am not drawing the arrows. Now, when these two switches are off, we do have the leakage current flowing in these MOSFETs. These are not ideal switches, even when the MOSFET is off, it does have some leakage contribution, and depending upon the technology, depending upon the dimension of the switches, the technology node, the dominant leakage component can be different. So, in the MOSFET we have several components of leakage, several ways in which the leakage current can exist. We have subthreshold leakage, we have junction leakage, we have gate leakage current. So, we have to see which one is dominant. If we talk about say 180 nanometer CMOS technology which we are using in our simulations, there the subthreshold leakage will still be relatively small, gate to substrate leakage is yet smaller. However, the reverse bias junction leakage can be pretty significant, and that is something which also increases proportionally with the W of the transistor. So, the subthreshold leakage for example can be reduced if we are having longer channel length, that imparts a relatively longer channel behavior to the MOSFET, and that can reduce the subthreshold leakage current. But if we are looking at the junction leakage for example, the junction leakage happens because of the reverse biased diode. If you are looking at the cross section of the MOSFET and you are having the gate terminal over here, say for the NMOS you have N plus drain terminal. So, I am just drawing the cross section. This is the gate terminal, this is the say the source or drain, and another source or drain. Now, we know that in the reverse biased configuration of the diode there can be significant increase in the leakage current across the diode, and here if you look at the conditions, suppose when the signal is towards the suppose when the signal is going up. So, you are having both the transitions in the signal. So, you have the upgoing slope and the downgoing slope of the input signal. So, you may be sampling the signal at this particular point, and after that the switch is getting closed, and you are expecting that the signal over here will remain constant at this point. And under that condition, if I look at the situation at the NMOS gate, you have overall gate voltage of the NMOS which is 0, you have the substrate generally which is connected to ground, and you have the signal which is sampled over here which is sufficiently low. Suppose the signal over here is sufficiently low. So, in that case of course the reverse bias for the drain or source to bulk junction for the NMOS will be relatively low, whereas if you look at the PMOS. So, PMOS substrate, it will be connected to say VDD, it will be having the PMOS substrate in general connected to the VDD, and the signal is low. Here we have for the PMOS which is having a P plus junction over here which is relatively low, which is equal to sampled value over here, whereas the substrate junction is VDD. Therefore, the reverse bias across the P plus N junction for the NMOS is going to be stronger in this case. What do we expect from there? You will have significant reverse bias current flowing from the substrate towards the source drain terminal of the PMOS over here. As a result, this can lead to increase in the overall sampled voltage, right. So, what we expect here is that you are going to get a slight increase in the sampled voltage, rather than being constant it will show some increase, and then next time when you are putting the switch on, again it will go towards the new value, again depending upon the condition of the switches over here it can show increase or decrease. So, when the input signal is low or the sample value over here is pretty small, close to ground, then the reverse bias current of reverse bias junction leakage of the PMOS is going to dominate, and it is going to increase the sample voltage a little bit. Let us see what happens when the condition is reversed, when the input signal sampled over here is high. So, suppose you are going towards the upper side. So, this is a high value. Under that condition, as we said, the body terminal of the MOSFET is 0 and the body terminal of the N MOSFET is 0, whereas the sample signal is high. In that case, the N plus drain of the NMOS is having a potential which is sufficiently high, whereas the body terminal, which is P, is low, is ground. Under that condition, the N plus P junction of the NMOS is going to have strong reverse bias. Therefore, the reverse bias junction current of the N plus P diode in the NMOS is going to dominate, and therefore, it is going to cause dissipation of the charges stored on the CS, right. And that would imply that as compared to the sample value, we would expect that ideally this sample value should once again remain flat, but rather than remaining flat, it will go down little bit, right, and that will be determined by the leakage current, how low it droops. If the leakage current, junction leakage current is first larger, the droop will be smaller. So, this is the dark curve over here shows the actual waveform we will be getting. When you are going towards higher signal level, the sampled voltage can droop and deviate from the actual signal, whereas when you are going towards the lower signal level, the sampled signal stored in the capacitor can show a little bit of increase. This is true when your junction leakage is a dominant component. So, this is if you have subthreshold leakage becoming dominant, then the picture can be a little different. So, your subthreshold leakage happens between source and drain, and in that case it will become beneficial because the signal will be able to follow the CS will be able to follow the signal over here, and in that case if the signal is going up little bit, the signal, the data value over here will be just trying to follow it because the subthreshold conduction is happening in this way, and likewise the signal is going down, the data over here will be also going down along with the signal. So, if you are looking at scale technology nodes, say 45 nanometer or lower, there the subthreshold conduction can be dominant. There also, of course, the signal over here will change as compared to the sampled value, but at least it will be trying to follow the direction of the signal at this point. So, in this case, if I say that this is for the junction leakage being dominant. If I take another example where the subthreshold leakage becomes more dominant, there if this is the sampled value at a particular instance and we want this to remain constant, rather than remaining constant, it will increase little bit because the input signal is increasing. And likewise, if I talk about the other half, if I am sampling the data over here, here also we will have the same polarity because the input signal the next sample it is increasing, therefore, it will slightly increase, and if I am going towards the down glowing slope, it will just have the opposite effect. So, this is the case for subthreshold conduction. When the subthreshold conduction becomes dominant, this is the case where junction leakage becomes dominant. So, the technology we are using right now, there will notice that the junction leakage is going to be the dominant component, and what does the junction leakage depend upon? We can see that the junction leakage will depend upon the cross section area of the junction. And what does the cross section area of the junction depend upon? Which transistor dimension? It is going to be the W. So, if you increase the W of the switch irrespective of the L, if you increase the W of the switch, the junction leakage component will increase, resulting in more and more dissipation of the charge into the substrate from the PMOS or the NMOS. Therefore, these slopes will increase, and the deviation of the sampled signal from the sample data at the closing point, it will also increase, which can be highly undesirable. So, if I revisit my resolution requirement, if I am dividing my entire signal range, that is around 2 volt peak to peak range, into 15 millivolts intervals, I would not like the sample data to deviate by magnitude closer to 15 millivolt. That means, if the data droop or the analog droop or increase in the sample values close to 15 millivolt, we are losing 1 LSB of the precision, and we are going to get a data which is wrong by 1 interval. So, that is not desirable. We are going to lose 1 LSB of information. So, that we should make sure that this droop or increase that is happening because of the leakage component is lower than that 15 millivolt interval in this case. And these are the two things which is going to determine the choice of CS. for example, what is the sampling capacitor dimension. So, if I choose Cs to be too small, even if you have minimum size transistors, it will lead to larger and larger droop. If this, so in our case, for example, we are looking at relatively lower frequency, sampling frequency is low, and if I talk about the on resistance of even minimum size transistor in 180 nanometer CMOS technology, it will be not more than 10 kilo ohm. So, even if you look at minimum size transistor when it is fully on, either NMOS or PMOS, their values are close to 10 kilo ohm in 180 nanometer. So, R on we expect around 10 kilo ohm even if we are in 180 nanometer, few tens of kilo ohm max. So, the triode region resistor of the on switches will be in this order even if it is minimum size, and then we are having the on duration, the overall duration for which the data is supposed to be held is equal to the entire sampling duration almost. So, if you are trying to reduce this on duration, as we said, if we look back to our sampling discussion, if I am trying to squeeze this further, that means for almost the entire sampling duration or the sampling period, this capacitor is supposed to hold the data. So, in our case, the sampling period will be determined by the signal frequency content, and if you recall our signal frequency content for the neural potential that we have discussed, this maximum frequency content may be few hundreds of hertz, at the max say kilohertz, and as a result we would expect that the sampling frequency is say few kilohertz at max. So, suppose the signal content, the maximum signal content is say 1 kilohertz, and corresponding to that the sampling frequency that you are getting is 2 kilohertz. So, the Ts is going to be 0.5 millisecond, and then we are trying to make sure that 1 upon times the C that we are having, that is the time constant provided by this is small, this is the on on duration. Now, this is going to determine the charging rate. So, for the on, of course, this is the charging rate. If I look at I was talking about the leakage component, what is the leakage current over here. So, I mistakenly took it the on one. For if I talk about the leakage component, of course, I have to talk about the off resistance, and for that I have to look at the leakage resistance, the subthreshold resistance of this MOSFET, and that depends upon the R on R off ratio of that technology. So, R on is 10 to the power of 4, and R off for the minimum size transistor, that is going to depend upon the R on R off ratio provided by that technology, and then R off, if I estimate for a given technology, I have to look at the R on R off ratio, and for 180 nanometer I can have an R on R off ratio of around 10 to the power of 5. That means corresponding to this I can estimate what is going to be my R off for the minimum size transistor. It can easily be of the order of 10 to the power of 9. So, I have the overall R off, this is the R off R on ratio. So, for a given technology we have a given R off R on ratio, and that degrades as we go down the technology node. So, for 180 nanometer 10 to the power of 5 or even better can be feasible. For lower technology 45 nanometer it can go down all the way to 10 to the power of 4. So, if the R on is 10 to the power of 4, R off can be 10 to the power of 9, and hence I must make sure that that R off, that is the R off times the Cs, that is the discharge time, that is the corresponding time constant, that is much larger, or in other words this is much smaller than the sampling duration Ts. That is the condition we must make sure we are having. So, here if you look at the values, I would get Cs must be significantly larger than Ts upon R off, and if I just put these number Ts, we have 0.5 millisecond, and I have an R off which is maybe 10 to the power of 9. So, this gives us something like a picofarad. So, I have Cs should be sufficiently larger than 0.5 picofarad. So, if I am choosing a Cs of say few picofarad, I should be safe with respect to the leakage. So, these are just numbers taken from a given technology that we are using in simulations, and from that we can predict that okay, what is the required value of capacitor, and if you are going for minimum size transistor, and then we can see whether this minimum size transistor is also satisfying our required criteria for the on duration. So, in the on duration we have just discussed that the RC time constant provided by this switches should be lower than the overall on duration, and as a result we must make sure that this on resistance that we are getting is satisfying that condition also. So, if it is doing that, then we are going to choose the minimum size transistor as it is for our design. If not, then again we have to trade off between these two. We may have to increase the W by L over here, but at the same time we may have to choose a larger capacitance so that within the off duration it does not discharge. So, that trade off is always there while looking at the sizing of these transistors and the capacitor for the sampling. And we will also look into some of the non-idealities, that if you are trying to reduce the R on by choosing larger transistor sizes, what are the other issues or non-idealities associated with the switching of these transistors that can come into picture. So, let us stop here for a short break and see whether there is any question.